Good day, students. This time we'll be having our lesson in mathematics in the modern world. This is your instructor, Mr. Japheth and Nabaira. But before that, you have to take note of these important features of the E-module. The first one is the checkpoint. If you will see this feature across the E-module, it conveys that you have to check your progress. It could be a practice exercise, a drill, or a thought-provoking question that will solicit your answer to better understand the topic discussed. Another feature is the key to correction. This feature in the E-module will give you immediate answers to the questions that are posted in the checkpoint section. No explanations will be provided to generate your own justification of the answers, hence enhancing your creativity and critical thinking abilities. So you have to take note of the key to correction and at the same time the checkpoint section of the E-module because these two features might pop out in any parts of the E-module so that your progress will be checked. So I think you're now ready. So this time we'll be having E-module 1.1, patterns and numbers in nature and the world. So the learning objectives of this E-module are, at the end of this lesson, the student should be able to identify patterns in nature and regularities in the world, and apply the concept of patterns and regularities in solving relevant problems. In this modern society, how often have you thought about the appreciation of the beauty of the things around you? Have you also paused and pondered about the underlying principles that govern these patterns and regularities? As rational beings, we tend to identify patterns, consciously or subconsciously. Hence, recognizing them feels very natural. In this lesson, we will be looking on some patterns that occur in nature and the world, and of course, how mathematics applies to them. So first, we have to define what is a pattern. A pattern is an arrangement which helps observers anticipate what they might see or what happens next. Now, it is also a way to show what may have come before. Because when you study pattern, you will understand what might come before that particular pattern occurs. It organizes information to bring order where there is disorder. According to Nukon and Nukon 2016, mathematics is the study of patterns. Hence, those who use patterns to analyze and solve problems often find success compared with those who cannot. So see, mathematics is full of patterns indeed, and those who are expert in pattern finding might find mathematics easier than those who cannot. Let's try to examine some patterns. Studying patterns helps students identify relationships and find logical connections to form generalizations and make predictions. This according to Hoffman et al. 2018. Now take a look at this pattern and guess the next figure. What might be the figure behind the question mark? So the first figure is a square, the next figure is a circle with a square, and the third figure, it was reflected at the bottom. And in the fourth figure, the upper figure that is perfectly similar to the lower figure was gone. So what do you think will be the next figure? So let's see. What do you think will be the next figure in the sequence? Can you guess it now? I think you have an answer. So the next figure is a square at the bottom. Can you figure out why? This is because of the addition and deletion of parts. So we expect that the last figure will be a square at the bottom. Do you agree with me? Okay, so we'll be studying more patterns. Next, let's try another pattern of numbers. 96, 82, 69. What do you think is the next number in the sequence? Can you think of the next number in the sequence based on some patterns? So I think you have now your answer. It's 57. Because of the decrease of the numbers 14 and 13, so the next decrease will be 12, resulting to 57. So take a look. 96 minus 82 is 14. 82 minus 69 is 13. So basically, the next decrease will be a number that is 1 unit lesser than the previous one. So that will become 12. That's why 69 minus 12 will give you 57. Did you get it? Okay. This time we will examine another pattern of letters. So, in this pattern of letters, A, B, C, D, H, I, J, K, O, P, Q, R, what do you think is the next sequence of letters in the blank? If you observe the pattern A, B, C, D, the next letters are E, F, G, and it skips the 3 letters. Then it proceeds to H, I, J, K. Now eventually, after K, it skips again L, M, N. Then it proceeds to O, P, Q, R. So most probably, the next sequence of letters will skip 3 letters after R, which are S, T, U. So the next letters in the sequence are V, W, X, Y, because there is a forward order of letters, but it skips 3 consecutive letters in the pattern. Did you get it? Alright, so we now have our checkpoint. Please prepare something to solve this problem. Find the next figure in the sequence given using patterns. A, B, C, D, C, D, E, F, E, F, G, H, and then blank. 7, 12, 18, 25. And lastly, what is the next figure in the box with question mark? So you have 4 choices for that. You can pause this video and try to analyze and answer these questions first so that you can think. Maybe you can pause for 2 minutes, 3 minutes, or at most 5 minutes. And then you can play it again to view the correct answers so that you can compare if your answers are correct or not. Did you get it? So you can pause now the video and then answer it with your own. This is to practice your skill if you have learned the lesson of pattern finding. So I think you're done. Here is now the key to correction. In the first question, the next sequence of letters are G, H, I, J. In number 2, 7, 12, 18, 25, the next number is 33. And in number 3, so what do you think is the correct answer? A, B, C, or D? The correct answer is letter D. In number 3, you have 1 line in the first box. You have 2 lines in the second box. You have 3 lines in the third box. And most probably, you'll be having 4 lines in the last box. So that is letter D. Did you get it now? Alright, so this time we'll be moving on to some patterns in nature. Nature abounds in spectral colors and intricate shapes. The rainbow mosaic of a butterfly's wing, the delicate curlicue of a grape tendril, and the undulating ripples of a desert dune. Maybe some of you have already seen a desert. You can observe some patterns in its ripples. But these miraculous creations not only delight the imagination, they also challenge our understanding. How did these patterns develop? And what are the mathematical structures behind this pattern? So let's try to explore some. The first is the snowflakes. So here is the figure. This is very beautiful. So my first observation in this picture is that it has 6 arms. Now, as you know, no 2 snowflakes are alike. So how can a snowflake be completely symmetrical within itself, but not match the shape of any other snowflake? Snowflakes exhibit 6-fold radial or rotational symmetry, with elaborate identical patterns on each arm. So if you're going to count the arms of a snowflake given in the picture, it has 6 arms. And it also has 6-fold radial or rotational symmetry. Is it a coincidence? Or the number of arms of a snowflake can determine its rotational symmetry? So let's try to explore more. Well, when each snowflake falls from the sky, it experiences unique atmospheric conditions like wind and humidity, and these affect how the crystals on the flake form. Each arm is an exact copy of the other. So if you're going to observe the snowflake in the picture, you can see that almost 99% of each arm is exactly the same to the other arms. Each arm of the flake goes through the same conditions, so consequently crystallizes in the same way. And if they crystallize in the same way, most probably they will turn out to be similar. However, many snowflakes are not perfectly symmetric due to the effects of humidity and temperature. Now, since we're talking about rotational symmetry, what is a rotational symmetry? A figure has a rotational symmetry if it can be rotated by an angle between 0 degree and 360 degree so that the image coincides with the pre-image. Of course, when you rotate an object 360 degrees, then that will coincide with the original image of the object. But when you rotate the object and it coincides with itself before it reaches 360 degrees, then that object has a rotational symmetry. The angle of rotational symmetry, which can be computed by dividing n to 360 degree, where n is the order of symmetry, is the smallest angle for which the figure can be rotated to coincide with itself. For example, if you will rotate a certain object 60 degree, and if it coincides with the original object, then an object has 60-degree angle of rotational symmetry. What is that order of symmetry? The order of symmetry is the number of times the figure coincides with itself as it rotates through 360 degrees. For example, before an object reaches 360 degrees, it coincides with the original image 3 times before it reaches 360 degree. Therefore, the object has 3 as the order of symmetry. Did you get it? So for a clearer explanation by an example, so let's try to apply it to a snowflake. In the case of a snowflake, since it has 6-fold rotational symmetry, that means before a snowflake will reach 360 degree or will return to its original position, it will coincide with itself 6 times. That's why the order of symmetry is 6. And how are we going to compute the angle of symmetry? That is 60 degree, because 360 degree divided by 6 as the order of symmetry, that will give you 60 degree. And if you're going to observe a snowflake, it has 6 arms. So basically the number of arms has something to do with the order of symmetry. Did you get it? So if it has 6 arms, probably it has 6 as its order of symmetry. Let's try to examine other elements of nature. A starfish. Oh, this is a very beautiful starfish. Now, sea stars or starfishes are invertebrates that typically have 5 or more arms. These radiate from an indistinct disk and form something known as pentaradial. From the word penta, that means 5. That's why a starfish has pentaradial or 5-fold rotational symmetry. Again, observe the arms of the starfish. It has 5 arms. So our guess earlier for a snowflake with 6 arms has 6-fold rotational symmetry. A starfish with 5 arms has also 5-fold rotational symmetry. Are we observing a pattern now that the number of arms relates to its rotational symmetry. Now, its order of symmetry is 5. Why? Because if you're going to rotate a starfish before it reaches 360 degrees, it will coincide with itself 5 times. So if you were going to imagine rotating this, then it will coincide with itself 5 times throughout 360 degrees. And it has 72-degree angle of rotational symmetry. How do we come up with that? That is 360 degrees divided by 5, which gives you 72 degrees. We have another checkpoint, so try to pause, ponder, and analyze this question. This is a very beautiful flower. This is known as a spiderwort. Now the question is, does it possess a rotational symmetry? And if yes, what is the order of symmetry and the angle of rotational symmetry? So basically, you have now an idea of the order of symmetry because it has 3 arms. Now again, you can pause this video for 2 minutes or 3 minutes to think and analyze this question so that you can have better answers. You can check your answer after a while. You can play it again so that you can check your answers. Is that clear? So you can pause now the video. So I think you have now your answers. So this is now the key to your correction. Of course, it has a rotational symmetry. And what is the order of symmetry? It's 3. Something that relates to the number of arms. So it has 3 arms. Basically, it has 3 as its order of symmetry. Because if you're going to rotate it, it will coincide with itself 3 times before it reaches 360 degrees. Now, the angle of rotational symmetry is 120 degrees. So let's proceed. How do we come up with 120 degrees? 360 degrees divided by 3. And that will give you 120 degrees. So let's proceed. Honeycombs. Honeycombs are example of a tessellation. What is a tessellation? This is where a pattern is repeated until it covers a plane. Say for example, this honeycomb is a plane. A certain figure is repeated many times to cover the whole plane. But in a tessellation, it must have no gaps and no overlaps. Other examples include mosaics and tiled floors. If you're going to observe the honeycomb, what particular polygon was used? That is a 6-sided polygon, which is the hexagon. Now, this also involves packing problems like finding the optimal method, and it is one way of maximizing the given space. In mathematics or geometry, you call that as packing problems. Now, mathematicians believe that bees build these hexagonal constructions because it is the most efficient shape for storing the largest possible amount of honey while using the least amount of wax. See how brainy bees are? They use hexagons and use this pattern of constructions so that they will achieve the highest possible efficiency. Shapes like circles would leave gaps. Of course, when you use circles instead of hexagons, basically you cannot fill in spaces because there will always be a space if you will use circles in packing problems because they don't fit perfectly together, unlike hexagons that fit perfectly together. So they're very intelligent. Bees are very intelligent in geometry, right? So that is the wonder behind honeycombs. The mathematical structure is tessellation, and the other one is the packing problem to maximize efficiency. Let's also have the sunflower. See the patterns? In a sunflower, you will notice that there is a definite pattern of clockwise and counterclockwise arcs or spirals extending outward from the center of the flower. Now, scientists and flower enthusiasts who have taken the time to count the seed spirals in a sunflower have determined that the amount of spirals add up to a Fibonacci number. For example, if you're going to count the spirals in clockwise direction, those that are in color blue or dark blue, how many of them are there? Can you please count them? So there are 21 clockwise spirals, and there are 13 counterclockwise spirals, those that are colored with a lighter blue or sky blue. Now, 13 and 21 are part of Fibonacci numbers. And what is this Fibonacci numbers? We'll be discussing more of this in the next module, but observe this pattern of numbers: 1, 2, 3, 5, 8, 13, 21, 34, and 55. As you can see, the next number is determined by adding the previous two numbers. Like 3 is 2 plus 1, 5 is 2 plus 3, 8 is 5 plus 3, 13 is 8 plus 5, and the sequence continues following that pattern. Now take note that 13 and 21 are Fibonacci numbers. So who would think that a certain sunflower, a very beautiful sunflower, have this pattern of number, Fibonacci number? Another mathematical structure in sunflower. This arrangement allows the sunflower seeds to occupy the flower head in a way that maximizes their access to light and necessary nutrients. This is another demonstration of a packing problem in geometry that optimizes the available space. The same is true with the honeycombs, because the sunflower's arrangement of its seeds maximizes the available space. And that is another packing problem in geometry. So see how beautiful the sunflower is? It has two concepts: Fibonacci numbers and packing problems in geometry. Let's also discover the pattern behind Romanesco broccoli. Although this type of broccoli is rare in the Philippines, but this type of plant is so amazing. Look at the figures. The bigger broccoli has smaller mini broccolis. Now in the case of Romanesco broccoli, each floret, the small florets, are miniaturized version of the whole head's spiral. See, if you're going to examine closely each floret, that resembles the bigger broccoli. This means the entire veggie is a one big spiral composed of smaller cone-like mini spirals. In geometry, this concept is called fractal, because the bigger broccoli is composed of small florets that resemble the bigger broccoli. And what is this fractal? In geometric terms, fractals are complex patterns where each individual component has the same pattern as the whole object. And that is very evident in this Romanesco broccoli. If you're going to examine closely the mini florets, they resemble the bigger broccoli. Can you see it? If you're going to examine even one floret, that resembles the bigger broccoli. Now, fractals are infinitely complex patterns that are self-similar across different scales. So if you're going to observe the mini florets, they are similar to the bigger broccoli across different scales, because we have the smallest floret, we have a bigger floret, we have a smaller floret. They are created by repeating a simple process over and over again. It also has spirals. So see how beautiful a Romanesco broccoli is? And the mathematical structure that you can observe in this plant. We have another checkpoint. This is a leaf of a fern. Observe this element of nature. Now, what mathematical structure can you find in this figure? Again, you can pause the video for a while for you to think what concept in mathematics is evident in this fern leaf. So you can pause the video and again play it for you to view your answer. So I guess you have analyzed it very well. Here's now your key to correction. The mathematical structure that is evident in this figure is the concept of fractals is present because the smaller parts of the leaf are miniatures of the bigger leaf. See? Like the Romanesco Broccoli, because it is composed of smaller leaves that somehow resemble the bigger fern leaf. Now, if you can see other mathematical concepts in this figure, well, that is okay. That means that you're very creative and rational in thinking of possible patterns that you can see in some elements of nature. So take note of this. The world around us seems to be made up of several distinct patterns and regularities, evolving from various complex steps of formation. However, looking more deeply, we can see many similarities and resemblances. The numerous examples explained earlier have definitely shown linkages between patterns formed under natural conditions in nature and the mathematical structures and principles that govern them, hence producing intricate and intriguing designs. So that would be all for our module in patterns and numbers in nature and the world. So if you want to read more about the topics, here are the references of this e-module. For the online references, we also have this so that you can study more about the topics. These are also part of the references, but some of them are credits to the photos that were used in the e-module. So that would be all for e-module 1.1. Thank you for listening. Have a great day and God bless everyone.